again. In this video, we're going to look at the conditions and the formulas for the sampling distribution of a proportion and go through an example. Okay, so remember we had a categorical yes-no question, and so we're talking about a percentage this time instead of an average. Okay, so we have certain conditions that need to be met again, provided that the sampled values are independent and the sample size is large enough. The sampling distribution for p hat, the sample proportion, is modeled by a normal model with a mean of p and a standard deviation of this formula here. So the great thing is our mean is always equal to that sample proportion, like we saw in the simulation. And then here's a formula for the standard deviation. It's the square root of pq over n. Okay, and remember q is the complement of p. It's 1 minus p. So let's say p equals 0.3. Q is 1 minus 0.3 or 0.7. So 60-40, 30-70, 20-80, those are all complements of each other. Okay, so let's go ahead and summarize this. We're taking our distribution of p hat. So this is, remember, all the sample proportions. Proportions calculated from a sample. You could think percentage. Proportion is the decimal version of a percentage. So p hat, oops, I didn't mean to do equal sign. I meant to do distributed as normal with a mean of p and a standard deviation of square root of pq over n. Okay, so similar to our means, we had this square root of n in the denominator. So as n gets bigger and bigger, we're dividing by something bigger, so our standard deviation gets smaller. Okay, so now let's talk about the conditions. The first two conditions are the same, and the third one is different. Okay, so the first one is independence condition. So the individuals in the sample must be independent of each other. Okay, that means one can't be influencing the next. Kind of goes hand in hand with randomization. If you take a random sample, they should be independent of each other. And then also along with that is the 10% condition. That's also part of the independence. If we sample less than 10% of the population, we can also assume that the events or the people are independent of each other. Okay, so we'll just talk about what we need for these conditions to be met. Then the second one is the randomization condition. The samples must be randomly chosen, also to get independence. Then the third one we talked about in the last video. Instead of just a plain number for sample size condition, we use this success failure condition. And that's because it depends, the n depends on the value of p. If p is 0.5, you don't need as large of an n. If p is really towards 0 or 1, then you need a much larger value, much larger sample size. So the way it's phrased is the number of successes and failures. Remember, n times p is the mean of a binomial. That's the number of successes, and n times q is the number of failures. So you don't really have to worry about that too much, but just calculate this each time. So we're going to check this condition each time. Okay, so we're going to show our check. So let's do an example. Suppose 60% of all college students are either very satisfied or completely satisfied with their online shopping experience. Okay, so you know this is like a 1 to 5 and people marked either 4 or 5, something like that. You decide to take a nationwide random sample of 2,500 college students and ask if they agree. Is it reasonable to use a normal model for the sampling distribution of the sample proportion? Okay, so let's check our conditions and talk about what we need for each one. Okay, so for independence, okay, first of all, the college students would need to be independent of each other, right? So I'm not sure what they're talking about with an online shopping experience and how that relates to college students. Maybe it's something online textbooks or something like that. So college students should be independent from each other. So what I'm thinking is we should have a variety of private colleges, public colleges, 2-year, 4-year, regions, all those kind of things to be sure they're independent. We wouldn't want to sample only private college students, then we wouldn't get an example of all college students, just like we wouldn't want to do all community college students. So sample a variety of public, private, 2-year, 4-year colleges or college students. Okay, and then the other thing we need to check is the 10%. Do you think 2,500 is less than 10% of all college students? That's our population. And I would say yes. I don't think, I think there's way more, if we just add a 0, there's way more than 250,000 college students. So we can say 2,500 is less than 10% of all college students. Okay, 2, I'm going to run out of space here, but that's okay. 2 is randomization. Okay, we can do this one pretty simply just by saying we must take a random sample. Okay, and then success failure, I'm actually just going to go right down here. Success failure condition, n times p and n times q. So our n is 2,500. That's our n. And our p is we have to be given this percentage in order to do this. So in this case, it's 60%. And then 2,500 times 40%, because 1 minus 0.6 equals 0.4. So those are the complements of each other. So let's calculate this. 2,500 is a pretty big sample size, so I'm pretty sure this is going to work. That's 1,500. That's greater than or equal to 10, so we'll check that off. 500 times 0.4, oops, is 1,000. That's also greater than or equal to 10, so I'll check that off. Notice these two add up to the total, 2,500, because these two add up to 100%. So if you find one, you can do a little shortcut to find the other one. Okay, so is it reasonable to use a normal model for the sampling distribution? So yes, all the conditions are met, as long as we do these things. So we can use a sampling, or we can use a normal model. Okay, so now it says find the mean and standard deviation. I'm going to go ahead and define it also. So I'm going to do p hat is distributed as normal, because our conditions are met. And then we're going to plug in, we're going to use our formulas. Our mean is p, 0.6 or 0.60, either one. And our standard deviation is the square root of 0.6 times 0.4 over n. That's the formula PQ over n. Let me put this down. That's the formula square root of PQ over n. Okay, so I'm going to calculate that. And then we can draw it and we can find a probability. So square root 0.6 times 0.4 divided by 2500. Order of operations says multiply and divide from left to right, so we don't need any parentheses in there, and it's 0.0098. I'm going to round that up. 0.0098. Okay, so I want to keep 4 decimal places for technology. But I'm going to draw this out, and I'm not going to use that many decimal places for the picture. Okay, so let's go ahead and draw this. Usually your assignment will say define, draw, and then find a probability, or define, draw, and label. So I think drawing just really helps to conceptualize what's going on here, and labeling it too. So 0.6, I'll put 0.60 since we're talking percentages, so that's 60%. That's our population mean for college students who were very satisfied or completely satisfied. And then 1, 2, 3 standard deviations, 1, 2, 3. I'm going to round this to, since this is almost 0.01, I'm going to round it to 2 digits so I have a percentage. So this is going to look like 0.61, 0.62, 0.63, 0.59, 0.58, 0.57. That makes it easy to read this as a percentage. If you get too many decimals, it's hard to conceptualize anyways. Okay, so this is, remember, all of our random samples of size 2500, they would go roughly between 57% and 63% if the true proportion was 0.6 or 60%. Okay, so to label this, it's hard to label this concisely, but I want to get all the information in there. Okay, so this is really the proportion that were very satisfied or completely satisfied. A portion who were very or completely satisfied in samples of 2,500. Okay, so that reminds us the sample size, and it also reminds us that this is the distribution of all the possible random samples. Okay, sample size is important because that's going to change the graph, right? Our sample size determined our standard deviation, and so if we have a different sample size, we would have a totally different graph. Okay, so now we can put this into online statbook and we can find a probability. What's the probability that the sample proportion who agree that they're very satisfied or completely satisfied is at least 57%? Wow, this is going to be pretty big, right? Because 57 is down here. So this is going to be all this. Probability that the proportion, p hat, is greater than or equal to 0.57. Okay, now we put these numbers, or put our distribution into online statbook. So the mean is 0.6. The standard deviation is 0.0098. I want to keep that accurate for technology, and then we want above 0.57. And here you can see the graph really matches mine. For some reason they don't have the third standard deviation up here, but I'm pretty happy with that. So you can also cut and paste from online statbook and just put your label down below. Okay, so our probability is 0.9989. makes sense because, oops, let me go back to the notes. 0.9989 is our probability, and that makes sense because it's almost the whole thing, right? Okay, so that's saying if we take a whole bunch of random samples, all the possible random samples, then the probability of getting an average, a sample proportion of each sample being 0.57 is really high. It's 0.9989, okay? So we're going to be using this going forward, but right now we're just pretending we know what the sampling distribution looks like, or we're pretending we know the population parameter so that we can figure out what this sampling distribution looks like. Okay, so we'll do another example or two in the next video. I will see you there.